Hey everyone, welcome. Today we're looking at a Leetcode problem called Number of Equivalent Domino Pairs. It sounds a bit like a game, right? We'll break down what it means for dominoes to be and figure out how to count them efficiently. Don't worry, we'll take it step by step. Okay, so here's the official problem description. Essentially, we get a list of dominoes. Each domino is just a pair of numbers, like 1, 2, or 3, 4. The main idea is that two dominoes are considered if they have the same numbers, even if they're flipped. So a 1-2 domino is exactly the same as a 2-1 domino for our purposes. Our goal is to count how many pairs of these equivalent dominoes exist in the input list. We need to find pairs IDZJ where comes before in the list, and domino is equivalent to domino. The numbers on the dominoes will be between 1 and 9. Let's walk through the first example. We have the list 1, 2, 2, 1, 1, 1, 3, 4, 5, 6. Okay. Let's look for equivalent pairs. The first domino is 1, 2. Is there another one like it? Ah, yes. The second domino is 2, 1. Since the order doesn't matter, 1, 2, and 2, 1 are equivalent. That's one pair. Now let's check the others. We have 1, 1. Are there any other 1, 1 dominoes? Nope. Then 3, 4. No other. 3, 4. Or 4, 3. And 5, 6, no other, 5, 6, or 6, 5. So we only found that one pair, 1, 2, 2, 1. That's why the output is 1. Let's try another one. Input 1, 2, 1, 2, 1, 1, 2, 2. Okay. Let's see. We have 1, 2 at index 0. Then another 1, 2 at index 1. That's a pair. Now we look at the 1, 2 at index 0 again. Is it equivalent to the 1 at index 3? Yes. Another 1, 2. That's our second pair. What about the domino at index 1, which is 1, 2? Is it equivalent to the 1 at index 3? Yes, it is. That's our third pair. Are there any others? We have 1, 1, no other. 1, 1, no other. And 2, 2. Thus, no other. 2, 2s. So, in total, we found 3 pairs of equivalent dominoes. Index 0, index 1, index 0, index 3, and index 1, index 3. The output is 3. So how might we approach this? The most straightforward way, maybe, is to just compare every single domino with every other domino that comes after it in the list. For each pair we compare, we'd need to check if they are equivalent, meaning, do they have the same numbers, possibly flipped? This seems like it would work, right? But if the list of dominoes is really long, comparing every single pair could take a lot of time. If there are dominoes, we'd be doing something like n-squared comparisons. We should think if there's maybe a faster way. Okay, the tricky part is that 1, 2, and 2, 1 should be treated as the same thing. What if we could represent every domino in a standard, or way? A simple rule could be, always put the smaller number first. So, if we see 1, 2, it stays 1, 2. But if we see 2, 1, we transform it into 1, 2 as well. If we see 5, 3, we transform it into 3, 5. Now, if two original dominoes were equivalent, their canonical forms will be identical. This makes comparing them much easier. Now that we have the standard way to represent each domino, we can just count how many times each standard form appears in the list. We could use something like a hash map or a dictionary to store these counts. We go through our original list, convert each domino to its canonical form, and then increment the count for that specific form in our map. For example, if we see 1, 2, then 2, 1, then 1, 2, again, our canonical form 1, 2 would have a count of 3. So let's say a specific canonical domino, like 1, 2, appears times in our processed list. How many pairs does that create? Think about it. If it appears 3 times, k equals 3, we found 3 pairs in the earlier example. If it appears 4 times, you can match the first with the second, third, and fourth, 3 pairs, the second with the third and fourth, 2 pairs, and the third with the fourth, 1 pair, which is 3 plus 2 plus 1 equals 6 pairs. There's a formula for this. It's k choose 2, which calculates to k-1/2. So after we count all the canonical forms, we just go through our counts. For each count that's greater than 1, we calculate k-1-2 and add it to our total result. Here's a neat little trick we can use because the numbers on the dominoes are small, only from 1 to 9. Once we have the canonical form, say a, where is the smaller or equal number, we can represent this pair as a single integer. We can just calculate a10 plus b. For example, 1, 2 becomes 1 times 10 plus 2, which is 12. 3, 5 becomes 3 times 10 plus 5, which is 35. Even 4 works, becoming 44. Since the biggest number is 9, the largest possible encoded value is 9 times 10 plus 9, which is 99. This means we can use a simple array of size 100, indices 0 to 99, to store the counts, instead of a hash map. The encoded number acts as the index into our counting array. Okay, here's the Python code implementing that idea. The first version uses a dictionary, or default dict, and tuples for the canonical key. The second version uses that encoding trick with the array of size 100. Notice how in both versions, as we process each domino, we first figure out its canonical representation, either as a sorted tuple or an encoded number. Then, crucially, we add the current count of that representation to our num_pairs total before we increment the count. This directly counts the pairs. If we see a domino type for the first time, its count is 0, so we add 0 pairs. The second time we see it, its count is 1, so we add 1 pair, the one formed with the first instance. The third time, its count is 2, so we add 2 pairs, formed with the first and second instances, and so on. This avoids the separate step of calculating k-1-2 at the end. It's quite elegant. So how efficient is this approach? We only need to go through the list of dominoes once. Inside the loop, calculating the canonical form and updating the count takes constant time. So the total time depends directly on the number of dominoes. We call this big O of n, or order n time. That's much better than the n squared we thought about initially. What about memory? If we use a hash map or dictionary, the space depends on how many unique canonical domino types there are. Let's call that, so it's order k space. However, if we use the encoding trick with the fixed size array, size 100, the space we use is constant. It doesn't grow, even if the input list gets huge. We call that order 1 foot or constant space, which is fantastic. Since k is at most 100 here, even the hash map approach is effectively constant space in this specific problem. Alright, let's quickly recap the main points. The core idea was to handle the equivalent if flipped rule by creating a standard or canonical form for each domino, like always putting the smaller number first. Once we did that, we just needed to count how many times each standard form appeared. We saw a clever way to count the pairs incrementally as we process the list, or alternatively, using the formula k times k-1 divided by 2 after getting all the counts. And we also saw that neat encoding trick, turning a pair like a into a single number a10 plus b, which let us use a simple fixed size array for counting, giving us a really efficient solution in both time and space. Hope that explanation helped you understand how to tackle the number of equivalent domino pairs problem. If you found this useful, please hit the like button, consider subscribing for more Leetcode breakdowns, and feel free to leave a comment if you have any questions or perhaps a different way to solve it. And hey, if you're feeling extra appreciative, the Boba Fund link is always there. Keep practicing, keep coding, and I'll see you in the next video.